solve the problem. So 3 times 273, about 600, divided by 8.
You got it.
About what?
How about 1,024?
T2 is equals 1,024. What's the units on that, Mr. Sam?
Kelvin.
Kelvin. So if it gets above that, let's actually subtract 273 so we have an actual number that maybe you and I can understand.
751.
51 degrees Celsius. So if that temperature gets anywhere close to 751 Celsius, which is
Run.
really, really, really hot. Yeah, run. This thing's going to explode.
Yeah, so that's why they tell you not to throw a can of spray paint into a fire.
Otherwise it will explode.
Yeah.
Yeah, okay. Okay, we now want to just spend a brief moment in time, or a brief moments, talking about ideal versus real gases.
Mm-hmm.
No gas is ideal, but some are.
Very close.
Very close.
Hey, look at that.
That is correct. You see, you know, is your wife ideal?
Of course.
So she's absolutely perfect in every way.
Well, yeah.
Well, I disagree.
Well, she might hear this. I have to
met
say
her.
these things.
No.
What? What are you saying?
He has a wonderful, wonderful wife. All right, we are now laughing extraordinarily because I've insulted his wife. I didn't mean to come across that way. What I was saying, that his wife is wonderful, but she's not ideal. She probably has a flaw or two, maybe?
Maybe.
You probably have a flaw or two,
Perhaps, maybe one or two.
But you see, she's
I kinda
probably
smell funny.
close enough. You smell funny?
I smell funny,
Yes,
generally
actually
speaking.
you do, yes,
Yeah.
that's true. But you see, some glasses are close enough.
Yeah. Close
So
enough.
if they're close enough, it's good enough,
Yeah.
okay?
All right.
So, but real gases have two important properties, okay? And this is true of all gases, but some to a lesser extent than others.
Right.
So real gases have attraction. This is the most important one.
Yeah.
Traction for, I want to say themselves, actually for
Each other.
each other. Yeah, it's-
Like particles.
meaning an oxygen molecule is attracted to some degree to another oxygen molecule.
Right. And some compounds more than others. Oxygen probably
Yes.
not so much.
And they also they take up
Space.
They take
Space.
up some space.
Right. With ideal gases, we assume, one, that they do not attract to each other, and that they do not occupy any substantial volume. But some gases do attract and do take up some space.
So that's the key thing. You see, so if I have two oxygen molecules, we use oxygen as an example. Here's a little oxygen molecule. They're actually like two spheres joined together. And here's another oxygen molecule. They are typically moving past each other. And as they move past each other, they take no notice of each other because they have no attraction for each other. But in reality, there is a very, very weak force, which, if you recall, and this is a later discussion in the year, this is called a London dispersion force, or we like to abbreviate it in LDF. And so, but if you want this attraction to be minimalized, is that a word, minimalized?
Minimalized, yeah.
Minimalized. Then you would want, what conditions
Minimized.
would cause that, and minimize I think is the word, better word.
Yeah.
What would cause that to, what conditions of temperature and pressure would cause this to be a small factor?
Well, if we have a low pressure, then those molecules are going to take up a large volume, and they're going to be far apart from each other, so they're not going to be as
yeah, so if
attracted
you have
to
them
each
like
other.
this, and they're way far apart in a big container,
Yeah.
their chances of interacting are
Very nil.
nil. Also, what about temperature?
If we have a really high temperature, those things are going to be moving so fast past each other that they're not going to have a chance to look at each other.
All right, so if you want an ideal gas, so this is kind of comparing an ideal gas. If you want an ideal gas, gases are ideal at high temperatures and low pressures. So actually, any gas could be an ideal gas.
Mm-hmm.
For example, Mr. Sams, you could take iron. Iron? Is iron a gas?
Not at room temperature.
Not, yeah, there's iron in this room. That's typically a solid. But could you make iron gas?
Sure, heat it up high enough.
Get it super duper hot.
And that's good because we want ideal gases at high temperatures. So you get it really, 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 really,
But
really hot.
But actually, when we talk really hot, we're really, really hot compared to its normal boiling point. And so this would be obscenely high.
Like the sun.
Less, like in the sun, it would be an ideal gas.
Yeah.
But you see, oxygen in this room, its boiling point, I don't have it off the top of my head, but I do know that the boiling point is in somewhere near about negative 200 and, I want to say 30 degrees Celsius-ish. But we're here in the room at 22 degrees Celsius, so we are 250 degrees above its boiling point.
Pretty high.
That's really high. So it is going very, very fast. And so therefore it acts like, well, like an ideal gas. But a gas that would not be ideal that's in this room would be this one, the Mickey Mouse gas, which of course is
water.
Water. And you see the boiling point of, there's water vapor in this room, but when a water molecule in this room at 22 degrees Celsius
That's
or whatever
not much higher than its boiling point.
Well,
Wait, it's lower than its boiling point.
Yeah,
what am I talking about?
Because of evaporation. You see, when they see each other, they're going to attract each other. And actually, if you recall, this is a hydrogen bond, which attracts them together. It's going to hook up, and it's not going to act in an ideal way. Oxygen acts like very much an ideal gas, where water does not.
Right.
Water is a real gas, okay, where oxygen is ideal. Now, when I say that's at the conditions that we live at, room temperature and pressures and stuff that you live at wherever you happen to live.
Yep.
Okay. Now, one last thing on real gases, and that's hard to see because I didn't do that right. Okay, but there's actually a real gas equation.
It's kind of derived from the ideal gas law. If you look at it, you can kind of see some similarities. There's a P term, there's a V term, and then an RT.
So it's the same kind of a deal. And then we have this, it's hard to see, I know, but this is actually, we have just two new variables if you look at it.
Just a little A and a little B.
And a little B. And this is the table of A's and B's right here.
Yeah, guys, it's just like using ideal gas law, but you just plug in a value for A and B and just do some more algebra.
We introduced this to you just to show you that it exists, because I have never, ever seen it. Actually, that's not true, totally. I saw this in one AP test many, many years ago. They gave you the equation, they gave you the value for A, they gave you that for B, and you solved it. So this is nothing to memorize.
Nope.
I'm not even going to show you an example, because I believe that you can all do algebra. And so this should not be a terribly difficult problem.
Plug and chug.
Yeah, it's a plug and chug problem. So that concludes podcast 5.2.
Yeah, Mr. Bergman, take us out with a little harmonique.
Oh, harmonicas. Oh, I had it backwards.
He played it upside down. That's kind of cool. All right, guys. We'll see you in class. Goodbye.